As Nicholas said, my name's Rodney and this is Steve Zint with Guycon Pumps and Equipment. And what we want to talk about generally today is efficiency. As we weren't here for the whole day as far as the presentations, but I think there's a common theme as far as efficiency as farming because of inputs increasing and so forth. We have to look at that as far as every additional cost, and anything that you can possibly cut will help you in the long run. As we're all here, it's all about irrigation, whether it be crops, whether it be corn, cotton, many different things as far as having output. But one thing that we want to talk about is as far as more bang for your buck, as far as the overall more crop per drop. So for every drop that hits your field, you get as much crop as possible to get there. And what we want to talk about is efficiency. And the overall efficiency as more or less as far as all the inputs you put into it, whether it be the electricity cost or the fuel cost or anything into the pumping system, what you get out of it minus the losses, whether it be a hydraulic loss, mechanical loss, many different losses that you can occur throughout the whole system, what can you lose throughout the system? And one thing that you also want to calculate was not only the pump efficiency, but the overall efficiency or the wire-to-water efficiency of the pump, the motor, or your engine, many different things to look at. And also, efficiency shown as a decimal or a percentage, and that's how you can calculate your cost. And speaking of that, as calculations, I know it's the late part of the day and so forth, but one thing that we want to show is a little bit of calculations. And within those calculations is how you get some. It says, what does it take to run a certain system? As far as your brake horsepower, your gallons per minute times your TDH or your total dynamic head, times your specific gravity, but we're all in water as far as the irrigation system, divided by 3960, which is a constant, times your efficiency not only of your pump, but you can also do it as a system as well. So we have a equation for this system. Now we want to look at as an overall, as far as that we know brake horsepower, how do you get your efficiency? And there is a calculation very similar to the brake horsepower, but how you do it is your gallons per minute times your feet ahead times your specific gravity, which is always 1, divided by your 3960, which is your constant, multiplied by your brake horsepower. And you wonder, what does that come out to? Well, overall, it tells us when you start doing your calculations, what does it do to you as a whole? You can look at some of your efficiencies, and this is what we're going to do later in the presentation to show you what we can do, what it can cause. So to calculate your operating costs, I know there's a lot of formulas in here, but how you can calculate an operating cost on one system, say on one pivot that you have, or one exact well. So how you calculate this is your gallons per minute that you're pumping, your TDH, your total dynamic head, or your pressure, times 0.0746 times your kilowatt per hour cost, depending on where you're at. It fluctuates depending where you're at, divided by your 3960 times your efficiencies of your pump and your motor. This is all electrical costs. We don't really have the efficiencies of a diesel engine or a gas-powered engine or anything else like that. So what we're going to do, as far as just, there's so many different applications throughout the country, so we just kind of put a quick one together as far as 300 gallons a minute times 200 feet ahead times your 0.746 times 11 cents a kilowatt hour. I don't know what it ranges in your areas. We kind of put a ballpark to it, and this is the 11 cents per kilowatt hour, then times the efficiencies. So it's saying for every hour it's costing you $1.90 for every kilowatt hour that you produce, for every hour that pump's running. You think, well, that's not much. Well, you look at an average of, say, a irrigation season is 5 months, run nonstop 24 hours. So you multiply that times 3,600, that would be 3,600 hours. So it's costing you roughly $6,800 for one well. So you look at that conversely, if you look at the equation, that's a 76% efficient pump. So we looked at it at a 71% efficient pump. Depending what your needs are, that same calculation takes you out to $2.05. You're thinking 15 cents, that's really not much. Well, when you look at it, you add it up, and it brings to a total of $534 that you could have saved in one pump application. versus, I don't know how many wells that you have or could possibly have, but that could add up long term. So that's one thing that you could possibly look at. Here's another quick example. Actually, I did this about 8 years ago to a customer, and he's saying the price of a new pump is extremely high. The prices of a new pump is extremely high. Well, if you look at the correlation between the two, you have a 79% efficient pump versus a 70% efficient pump. So you go down the cost. Well, your brake horsepower alone, you have 31 horsepower versus 37 horsepower to produce the same amount of gallons to come to the top of the ground to feed you into your pivot, to your drip, or whatever your application is. So your energy cost on the 79% efficient is almost $3, which the other one is over $3. So all in all, in one season, it's costing you over $1,200 just in energy costs to run your system, to fill your pipeline, to irrigate your system. So that is a main key for something to look at. And once again, it's only a 5-month irrigation period that you're looking at. This is a little calculation that we put together as far as a program so you can compare systems. This is one last calculation, and I'll try to stay away from as much math as possible. But this is just a quick comparison, what we put in as far as 700 gallons a minute at 525 feet ahead. As you can see here, it's run 3,600 hours. We can change it to whatever you need to, whatever your demands are. We just think as an average, roughly a five-month season. And then we multiply it out times hours, because if you're watering corn, it's typically 24/7, 7 days a week within that time period. So what we did, we just left it run the whole time. And as far as the energy cost, we went ahead and put it at 11 cents versus this is actually close to a line shaft application. So therefore, it's a little bit higher efficiency as far as your pump. So you'd have an 82% efficient pump, and your motor, which is a vertical hollow shaft motor, typically are a higher percentage as far as efficiency, to 90% versus one that is 77%. I know it's a lot of wording and so forth, but if you break down to the lower portion, here's where all the meat and potatoes, so to speak, of the application is. Your overall pump efficiency of your pump and motor is 73% versus 69%. Then it breaks down to your horsepower. It's more or less telling you that you have more or less 113 horsepower on the efficient system versus 120 horsepower to run the same application. So you break it down a little bit further as far as kilowatts. It's taken roughly 28,000 kilowatts versus 29,000. Then it breaks down into your energy, how much energy you're consuming monthly and annually for this actual one application. Then it breaks down for every 1,000 gallons. It's taking you 25 cents to produce 1,000 gallons on one system versus 26 cents. You think, well, that one penny, is it really much? You break it down, the initial cost difference, and these are just ballpark numbers of what the actual just pump and motor costs. That's it. So your initial cost is $2,400 that you're saying, well, I can save that on this this other pump. Well, if you look at your efficiency as a total, if you run this within the 5-month period, you're saving $200 a month, or $2,400 a season. And more or less that pump will pay for itself in less than a year. So it's something to look at as far as efficiency as a whole, as a system. So efficiency as a whole does matter. And that's one thing that you need to look at, because as it was mentioned earlier, you need more crop per drop. You need to make sure you get the most demand out of your crop or your field as much as possible while pumping the system. Things to look at when sizing whether your well, whether your pump. The majority of these are probably downhole, but need to double check you are getting an efficient pump. You know, I've been in this industry probably going on 15, 16 years, and I've talked to certain guys. They said, well, my granddad is putting in a 40 horsepower, so I need to put in a 40 horsepower. Well, we need to start looking at things, because well logs have dropped, waters has dropped, and therefore you could be using that 40 horsepower to pump only 20-gallon-minute water. So therefore you have all that extra horsepower sitting there and not moving any water, moving any more water, and all you're doing is sending your more additional money to the power company. Also, as far as if you're looking at line shafts or submersibles, one thing to look at, you need to know your drawdowns. As it was mentioned, I can't remember the gentleman that mentioned earlier, you need to also look at what are your conditions, because it does drop down from time to time. And throughout the year, it does change your conditions, and it does change your horsepower of what your pump is using. You need to know the gallons a minute that you need for your system, whether it be your pivot or whether it be a drip irrigation. You need to understand what your needs are, because if you oversize a pump, there's many different things you can run into, which I'll talk about here in a minute. But you need to know your pumping level, be aware of what your well logs are doing and so forth.